Okay, good. So, 10, I guess. Time. I'll start like I did for space with some conceptual points, crucial for not to be confused. And then I'll introduce the main tool, the Hamilton function, and the way we deal with time in quantum gravity. And there is a part of this initial discussion which is completely parallel to space. In fact, it was the same historical development. So let me start from there, and let me start, as I did for space, for distinguishing notion of time. And actually, let me anticipate by that. All the confusion which is in the literature about time comes from mixing different notions and calling with the same name different things. We call time different things, or more precisely, the usual notion that we have, the intuitive notion we have about time, it's a very rich notion. It's very stratified. There's a lot of has a lot of pieces, and it's by not disentangling them that confusion arises. I've written a book about time. It came out in Italy a few months ago. It came out in French today. Is the day is coming out, and it's coming out in English next week or so, in a couple of weeks. And the title is The Order of Time, which I discussed time and temporality at large. I'm not going through what is this book here, but the key ideas are needed for quantum gravity. So, first distinction, going back as I did for space historically, there is a relational notion of time related to the question when. We talk about time when you ask the question when, and we answer by saying tomorrow, when the bell will ring, when it starts raining, in 3 days, when in 10 minutes. Each time we answer to the question when, we are referring to some happening, some things that happen at the same time. So we locate eventment. How do you say evènement? Events, thank you. French and English get confused in my Italian mind pretty usefully. Events, one with respect to the other temporary. So things happen in the world. The world we experience is not a world of objects, it's a world of events, of processes, okay? And these processes are next to one another, together with one another, and this relation of who is next to whom and who is together with whom is what we call time. That is the way, again, Aristotle described time in great detail. He has a famous definition of time, which time is the order of change, is the number of change with respect to the before and the after. So, if you think for a moment, it's like space. It's a way of numbering change, which means that if nothing changes, there's no time, right? If time is just a way of numbering, calling things that change, if nothing happens, there's no time, because time is just the change, the calling of and Aristotle discussed that explicitly. He even says, well, imagine that I'm in a dark room and nothing moves and I stay completely still. Is time still? He says, no, it's not still, because nevertheless my mind is thinking. I mean, there's always some process going on, and what I call time is this process, nothing else. And that's this, time is numbering processes, events, processes. And then Newton came, and exactly the same books, the same page where he gives this discussion, where he introduced this Newtonian time, this Newtonian space, which is there even if nothing is there, and which can be empty. He, in parallel, introduces his Newtonian time, and once again, he does not say Aristotle is wrong, or Descartes is wrong. Descartes has the same idea of time. He says there is that time, which is the vulgar time, the common time, what everybody calls time, but there is something else. There is the absolute time, the true time, or what we call the Newtonian time. And that's a variable that passes by itself, whether or not anything else changes. So if you freeze everything, nothing moves, you don't think, nothing oscillates, everything is Newtonian time, just keep marching ahead by itself, and is there, irrespectively of any other event or process which is happening. There are two very, very different ways of thinking about time, and the important point I want to stress is that, as Newton says very clearly, is not or either one or the other, as in many discussions. This is always there. And Newton says, besides that, which is the usual way we use time, when we say, I'm going to talk for 45 minutes, it means that this is going to move 45 minutes here, and when this gets here, I'll stop talking, if all goes right. So we're referring to this. And quite importantly, Newton, when he introduces Newtonian time, he says very clearly, this is not directly observable. I stress that because Newton theory became so effective and so common and so much told in school that we tend to think that Newtonian time is our direct perception of time. Newton says very strongly and clearly that his time is not perceived, cannot be perceived, cannot be detected, can be computed out of the movement. In fact, he said the time t, you need the astronomers to tell you how things move, because the usual time is days. But the Earth doesn't make a tour at the same speed. If you watch carefully the astronomers, the time it takes the Earth for making a tour changes. So that's not the true time. You have to correct it. And Newtonian time is a mathematical abstraction that you extract from a lot of computation, such that when you evolve things with respect to this time here, things follow beautiful Newtonian equations, F equal ma. Okay, so that's Newtonian time. Which means, and that's a key point, that let's do the standard elementary physics. I do a pendulum. Okay, so I have something that oscillates, and I study this angle, alpha. And the way you usually think about this is that the theory tells me how alpha changes with respect to time. So given initial condition, Newton equation tells me how to this oscillates. But if you think for a moment, what is really going on? What is really going on is that I have this, and I have my clock, which gives here an angle beta, which I call time. This is time. So I'm making a table. I have alpha and t, and I see how the two change. Let's call it beta. And this change in time, but I don't see time. I only see this angle and this angle. I see the clock, not the absolute time. So I have alpha of t and beta of t, but I really only see alpha of beta. The abstraction time is useful for parameterize the relation between this angle and this angle. I always have clocks. I never have direct access to time. And what is a clock? Well, it's a process designed to be as close as possible to this Newtonian ideal time. Of course, it'll never be perfectly so. But so Newtonian time is not directly observable, but it's approximated by real clocks. Now, once again, when Einstein starts working with special relativity, it does not change this idea of an existing Newtonian time. It just merges this Newtonian times with Newtonian space. So it brings them together in Minkowski space. Time. And when it does in 1915 GR, this becomes a field, the gravitational field. And a clock is precisely an object whose dynamics is such that it reads out along his word line a feature of the gravitational field. So a clock is in space-time, you have something that moves, and here you have a little pendulum, and it pendulates, and it ticks at units of its own time, which are just a measure of an aspect of g mu nu, of the gravitational field there. So this makes very clear that the clock just measures an entity, and this entity is in fact there as Newton had the correct intuition is, but it's not something over and above the stuff of the world and its processes. It's just one of the things of the world, which is the gravitational field, exactly like we did with space. So the Newtonian times is reduced to one variable of one of the ingredients of the world. So far so good, and so far it's completely parallel to space. But of course, there's something disappointing here, right? There's something missing. And the obvious question is, well, if this t variable is just one of the variables of the world, why it behaves so differently than the other? I mean, why, let me put it very stupidly, why can we go back in space but not go back in time? I mean, why it flows? Why we are here and then there and then there and then there? So there seems to be aspect of time, of temporality, which are not captured by this distinction, and more than one. One is irreversibility. And one is that it sort of passes, it flows. And, we remember the past, we don't remember the future. The past is fixed, the future is open. Compute probability of the future, we don't compute probability of the past. So what is missing? And this is a long discussion to try to understand where this aspect of the world come in. I'm only sketching it. The key observation is that irreversibility is not in mechanics, is in thermodynamics, right? So all phenomena where there is no heat are reversible, or something analogous to heat are reversible. Heat has to do with macroscopic variables, so have to do with statistical mechanics. So irreversibility comes in statistically, that we know from elementary courses, foundation of thermodynamics and statistical mechanics. And we actually understand pretty well the reason of the second principle of thermodynamics, up to a mystery, which is why entropy was low in the past. Nobody so far has given a decent explanation, convincing, of why entropy was low in the past. Somebody says, well, entropy was low in the past because there's a law that says that entropy was low in the past. Good. It's fine. But entropy is such a complicated thing. It's just a number of microstate corresponding to a macro state. Why has to be low in the past? I mean, it's just... somebody tried to tie it to cosmology. I've never got convinced to that. I have a paper on that, which I'm not going into, trying to understand that in a perspectival way. So it's not the universe which is low entropy, it's the macroscopic variables we use are such that we see that. I'll leave this, yes?
Saying, to ask the question why entropy was low in the past is equivalent to say why entropy is growing.
No, absolutely, not at all. If you have a statistical system, you choose a macro state with low entropy. Okay? To this macro state correspond a large number of microstates. Almost all of them, if you evolve with the classical equation of motion, their entropy grow in the future and in the past. Okay? So if entropy is low at some point, if we evolve, it's pretty obvious why it grows. Because unless we're extraordinarily unlucky, we don't know the microstate, and almost all the microstates evolve. What is mysterious is why in our real world, if you go backward, this doesn't happen. Why, if you go backward? And in fact, in concrete situations, you understand why it doesn't happen in the past just because the entropy was lower in the past. Just because if I take a box with gas half compressed and I let it go, the gas expands. Okay? Now, if half the way I take a picture, the gas is just not fully expanded, and I ask on the basis of my picture where the gas is going is expanding. But if on the basis of this picture I ask what does the equation of motion backward would tell me, also is expand. So this means that that particular state is a very strange state. Why is strange state? Because it comes from a low entropy one. Now, why was a low entropy one? Well, because I experimental compressed it. But why I could do it? Because I had low entropy. And why I had low entropy? Because I ate food with low entropy that come from the sun, which has low entropy with respect. And why the sun has low entropy? Because it's burning hydrogen into helium, and the hydrogen has less entropy than helium. And why it has low entropy? Because it comes from a cloud which have even lower entropy. So the more every time you follow, you discover that the more you go backward, the more you are in an improbable situation. So you completely understand what's going on, except the fact why everything started in an improbable situation. That is the mystery of the second principle of thermodynamics. That's the only mystery of the second principle of thermodynamics. Boltzmann K theorem is correct. It's just asymmetric.
Is this true statistically, or it can be violated like once in a million?
It's statistical.
Statistical.
Oh, it's statistical, yes. But, the Avogadro number is whatever it is, so it's a statistical thing that for us, you can bet all your money safely on it. I mean, you can bet all your money that the gas in this room is not going to compress now and go in a corner. It could, of course.
If you live infinite time, good.
Right, but we don't live infinite time.
Yeah.
Yes?
You said all of these mysteries at that time just boiled down to the thermodynamic arrow. How do you...
No. I'm saying all the mysteries about irreversibility... Oh, sure, you're anticipating to the next one. Yeah.
Yeah, the psychological arrow.
Yeah. I'm getting to that. Now, once we have understood this, or not understood this, I mean, grant me that entropy was low in the past. Okay? It's a fact. Maybe it's because we chose this microscopic observable, maybe it's perspectival, maybe it's a law of nature, maybe because God created the world in low entropy, maybe because Shiva did that, whatever. Grant that to me. Immediately after, let's go back to all the funny phenomenology, like why we remember the past and not the future. There's only one answer, because entropy was low in the past. It's not obvious, the steps. But because in a gradient of entropy, you can show that you can have traces of the past and very unlikely to have traces of the future. If you think about it, there's nothing else that could explain it. The reason there are things which are written here, which I interpret as written last year and not next year, is because of entropy was low in the past. Right? Because mechanics is time symmetric. The reason we have memories of the past and not memories of the future is because entropy was low in the past, nothing else. So all the phenomenology around us which break the direction of time, it's all related to that. There is nothing else. Okay? Including quantum mechanics. There's a lot of confusion about quantum mechanics. We say that quantum mechanics, the state changes as a measurement, and so we measure spin, say z to be plus at some moment of time, and then we say the state, remember that until next measurement. That's just perspectival. Quantum mechanics does not distinguish the past from the future. If I if I have a sequence of Stern-Gerlach experiments, and I look at a sequence of measurement, and I give you the results, and I do this many, many times, so you can compute all the probabilities. You cannot know the direction of time. There's no way to see if time goes this way or that way. Quantum mechanics is blind to the direction of time. You cannot predict the future in quantum mechanics, but there's a beautiful paper by Einstein on that, little known. You cannot predict the past either. Given the state today, if you want to know what was the state yesterday, you have just a probabilistic prediction. The reason you can do better prediction in the past than in the future is because there are traces, and there are traces because entropy was low in the past. So this has nothing to do with mechanics, has nothing to do with quantum mechanics, has nothing to do with quantum gravity. Because there are traces in of the past, our brain uses these traces a lot. We have memories. Since we have memories, we perceive the past as fixed and the future open. But this is a perception. There's no more openness in the past and the future than the fact that there are traces. And traces are there because there's a gradient of entropy. Right? So where does the flowing of time comes in? Well, the flowing of time, the passing of time, if it has to be understood at all, it's going to be understood by understanding what happened in our brain and in the way our brain works. There's a beautiful book recently by people studying the brain, Dean Bonomano, and the title is Your Brain is a Time Machine. So the way the brain works is it uses a traces of the past, memories, to predict the future continuously. So this gives us a awareness, we don't know what awareness is, but awareness of some span of the past and some span of the future. We have memories of our life, we have collective memories of civilization, we have history. So we have this vision of time, past, a lot, and glimpse of the future because we try to do predictions. That's the flow of time for us. Okay? This has nothing to do with quantum gravity. This has nothing to do with mechanics. This has nothing to do with quantum mechanics. It has to do with brain, has to do with aspect of the brain we have difficulty of understanding, like consciousness and that kind of stuff. Has to do with thermodynamics, have to do with statistical mechanics, not with quantum gravity. That's the point. That's the key point. So, disentangling thing. And pretending that in quantum gravity there's an explanation of the flow of time is is asking the wrong question to the wrong. Like is asking, a red t-shirt is more vivid than a gray t-shirt or a blue t-shirt. Why? Let's ask physics. No, it's not physics. I mean, these are two different frequencies. You have to ask psychologists. You have to ask people about who study the particular detectors we have in our eyes, or maybe the history of our species that were red berries in the wood and we had to find them. That's the question. That's where you have to ask the questions about why red is more vivid than gray, not physics. Well, it's always physics, but it's levels upstairs of complexity. And so very often people ask quantum gravity questions about the flow of time, about the difference between past and future, which don't pertain to quantum gravity, pertain to a completely different domain. In quantum gravity, you have events, processes. No doubt you have processes and events, because that's how the world works. It's not things, is, if you want, it's not things in space, it's things in space-time. It's that things that last for a while, okay? It's a process. You can number them, and the convenient way of numbering them is proper time. Of course, proper time is along a world line. It's not global. There's no common time in the universe. We know that from general relativity. So forget about a common time in the universe. It's nothing like that. There's no preferred direction back and forth. There are many different times that go at different speed. There is special relativity. So because of special relativity, there's no simultaneity well-defined at a distance. Simultaneity is an approximation. The notion of simultaneity is an approximation due to the fact that we don't perceive the speed of light. So I see you, you see me, and we are simultaneous, but just we can neglect the nanosecond light takes to go back and forth. So we have clocks, we have processes, we have no direction of time. We don't need to talk about flow of time or anything like that. And what we can compute in the classical theory is, given some initial something, how this evolves. In time, no, how it evolves, how the variables evolve one with respect to the other. And in the quantum theory, given some values, we can compute the probability of some other values, how they are related to one another, one of which could be the proper time if you have a clock measuring it. So that's the structure. No preferred time variable, no preferred direction, no flow, yes events, yes local clock times, yes the gravitational field, And I've sort of discarded the irrelevant notion and kept the relevant notion. Questions? And now I have to put this in for real. So far it's blah, blah, blah. Okay, now I have to make it. You have a question?
Yes, I think that to me there is something feature of that distinguishes time from space, which hasn't been mentioned here, which is some kind of a predictability, in the sense that, forgetting about irreversibility, let's say I can travel to the past or to the future, doesn't matter, but it's still the case that if I know a space-like surface, I more or less know the next one or the previous one, whereas if I know a time-like surface,
Yeah.
I cannot predict anything
Yeah.
sideways.
Yeah, absolutely. So sure. This is a basic aspect of an elementary aspect of temporality, which is part of it's in physics. Absolutely, I don't want to deny that at all. So if you have a set, if I know the state of things here, I can compute it at least in the future light cone. Let's think classically for a moment. If I know the state here, I can classically uniquely predict everything what happened here and uniquely predict everything that happened there. Absolutely. So if you have values here, 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 and here, you don't know. There's no dynamical equation that tells you what happened here. If you have a surface here, you cannot deduce. But if you have a three-dimensional surface, then you can compute there. So that's definitely, that has to be part of the story. And in another way of viewing this, if this is an initial surface, three-dimensional surface, this is a final surface. This is in the future is the final is within the light cone of the future of the initial. Then classically, given the data here, I can predict the data here. Quantum mechanics, given the data here, I have a probabilistic prediction of the data there, and that's exactly how we're going to work. So the way we're going to work is to have our quantum states sitting here and here, and have a amplitude that tells the probability of this couple, of if you want, the probability of these given this, or the probability of the two together. So we'll have an initial state, a final state, and with an amplitude of going from here to here, or if you want, an amplitude of the of the tensor of the two. The spin network sit here and sit here, and we need to compute amplitudes associated to spin networks. That's exactly what we're gonna do. The space, so the tensor product of the initial and final state is called the boundary Hilbert space, and the dynamics is going to give an amplitude to any boundary state. So at the end of the day, the dynamics is just going to be a bra on the Hilbert space that I gave you, interpreted as spin network sitting here and here. Where is time? Well, we don't need time. Time is in the variables themselves written here, because these include the gravitational field, and any clock is a function of the gravitational field. Let me give the same picture in a slightly different manner. Suppose this is a region of space-time now, so I have some time-like boundary to make it more clear. And suppose I'm doing some scattering experiment. I'm CERN, I have some particles coming in, some particles going out. Usually we think, well, there's a state that says there's a particle here, and then some particles go out. And the state tells me where is the particle in Minkowski space-time, and how much time goes from here to here in Minkowski space-time. So I have some t and some x that tells me, okay? Then you don't use x, you Fourier transform, use k, so that's a k of the Fock space states, and that's a t of the e to the ht, which is the evolution. But now let's do that relativistically, in general relativity. So here we use Minkowski space-time. That Minkowski space-time is a gravitational field. So let's do that in general relativity. So in general relativity, now we have to give the fields all around the boundary here. So in particular, I have to give the gravitational field all around here. But if I have the gravitational field all around here, I have the state of the gravitational field all around here. The distance, it's just the value of the gravitational field here. And the time is just the what I wrote before. Is the integral along this line of square root of g dx dx. So it's the integral here. So I don't need to give a time or a position. I just need to give the gravitational field and where the particles are with respect to the gravitational field. So I'm going to give spin network and where the particles are on the spin network. Spin network is the space-time. Minkowski is the thing we are discussing. And once I have the boundary states, I need this W, which intuitively you can think as Lafayette as a path integral, as the integral of all possible space-times, plural, inside. So I'm doing the functional integral inside that fixed boundary condition. The boundary condition including the g mu nu, and therefore there's no extra space and extra time needed, right? I have relational space in the sense of Aristotle, no Newtonian space in the sense of Newton. Let's do a little bit more precise. Let's go back to.
And so the name initial and final there is a little bit misleading.
Yeah, a little bit misleading. In fact, we don't want to think much about initial and final.
Just a global state
Yes,
on
right.
the boundary.
That's right.
And then
That's right. That's the proper way of thinking. That's right. That's right. Good. Now let's try to do this a little bit more cleanly. Let me start by reminding you about a classical quantity, which is the Hamilton function, which plays a role in making this, in formalizing this a little bit cleanly. Let me start with the standard Hamilton function, or principal Hamilton function. What is a Hamilton function? Is a function or variables which can be defined as follow. Imagine you have a system. So this is standard classical mechanics, finite dimensional classical mechanics. So you have some variables. I want to use the same notation here. Some variable q evolving in time. So this is, let's go back to the standard time thing. And we have equation of motion given by a Lagrangian, which is a function of q and q dot. Okay. So you have an action, which is the integral of dt of the Lagrangian, q of t, q dot of t, and if you vary this is the action, and the action is a functional of the trajectory. So you have a trajectory in space-time of the particle. So this is t, this is q, and the particle moves. Now, if you vary the action and you put it to 0, you define the equation of motion, and you have some solutions of the equation of motion which satisfy the Euler-Lagrange of that. If this is the standard thing, the solutions are uniquely determined by the initial position and the initial velocity. Okay, or up to degeneracy, they can be determined by the initial position and final position. So let me choose an initial position, Q0, at time t0, and a final position, Q final, at time t final. And generically, let's say, I'm going to generalize for a more general case. Let's say that there's only one solution of the equation of motion going from here to there. For a free particle, there's always one solution. So given this full number, Q0, T0, Q final, T final, there will be one solution of the equation of motion, and this will have an action. So I can write a quantity which I call S function of Q0, T0, Q final, T final. Okay, careful, it's not a function of trajectory, it's a function of 4 variables, which is the integral, is the action, so the integral of the Lagrangian in dt of the actual solution of the equation of motion determined by these 4 numbers here, Q0, T0, Q final, T final. Q0, T0, Q final, T final. So given these 4 numbers, I can compute a single number, which is just, I solve the equation of motion, and this is called the Hamilton function. And it was introduced by Hamilton in a remarkable paper in which he said, if you know this function, from there you can compute the solution of the equation of motion generally. You probably have seen this in Hamilton-Jacobi theory. In the paper, Hamilton has this marvelous phrase in which he says, Mr. Lagrange function, the Lagrangian, defines a mechanical problem. Mr. Hamilton function is himself solves the mechanical problem. Of course, it's not easy to compute the Hamilton function because the knowledge of the Hamilton function is in fact equivalent to knowledge of the solution of the equation of motion. Why? Well, it has all sorts of beautiful properties, the Hamilton function. So I want to talk about the Hamilton function a little bit because it's it generalized to a relativistic system. It talks to the quantum theory directly. It's very beautiful. The first property is that the derivative of the Hamilton function, so Q initial, T initial, or Q final, T final, or 0, with respect to Q initial is momentum, is initial momentum. It follows directly from its definition. The derivative with respect to Q final is P final. The derivative with respect to Q initial, T initial, Q final, T final. T initial is the energy. In fact, is minus the energy, the initial energy. And with respect to T final is minus the final energy. Now, if you think for a moment, this property here is sufficient to to show that if you know it, you know the equation of motion because you just invert it. When you compute this derivative, you have the P initial as a function of Q initial, T initial, Q final, and T final. So if you know this function, now you can invert it and write Q final as a function of what? Of Q initial, P initial, T initial, and T final. So you have Q as a function of the initial data and time and T. So you have Q as a function of T. Right? So if Hamilton was right, If you know this function, you know the general solution of the equation of motion. You know the position as a function of the initial data and the time lapsed. But there's something particularly clean in the Hamilton function formulation, which is that it treats the two variables q and t on the same ground. You see, in the Lagrangian formulation, t and q have a completely different status. T is the parameter in which you evolve, q is a variable. So it's clearly an evolution of q and t. In this language here, you just q and t, and they are. You don't need to say which one is time, which one is the variable. You just have one quantity, function of the initial data including time and the final data including time, and that captures the everything you need. How do you find it, the Hamilton function, without going through the Lagrangian? Well, another property of the Hamilton function is it is a solution of the Hamilton-Jacobi equation. So instead of going through that way, you can directly characterize a quantum system by the Hamilton-Jacobi equation, which is a property that the Hamilton function satisfies. And the Hamilton-Jacobi equation is ds over dt is equal the Hamiltonian of q ds over dq. It's an equation for the Hamilton function, its derivative with respect to the various variable that you know if you know the Hamiltonian. Now, you can write this slightly different. You can write it as c of q t ds over dq ds over dt equals 0, just by treating q and t on the same ground, where this function c is basically this one. So c of q t, sq st is just st minus h of q and sq. So, but this is the Hamilton function written in the way you usually write the Wheeler-DeWitt equation. What I'm saying is that the Hamilton function by itself doesn't necessarily distinguish time derivative by space derivative. It's just an equation for the Hamilton function, the variable, and the derivative of the Hamilton function with respect to the variable. This is a formalism which treats the independent variable and the dependent variable on the same ground. So it does not demand you to ask which variable is the time variable. And that's exactly the situation in which we find ourselves in general relativity. In general relativity, the time is a clock time, is an integral of g mu nu, so it's hidden in the component of g mu nu. So we don't have it separate from the other variables. What the Einstein equation gives us is how the various components of g mu nu and matter and everything evolve together. So here, think of the dynamics as two variables, q and t, that evolve together, and the Hamilton equation, the Hamilton-Jacobi equation as the equation for this together, this set of variables, q and t, which define the Hamilton function, which knows everything about the classical equation of motion. Now, what is the relation? Why this is crucial? Because that talks directly to quantum mechanics. In quantum mechanics, you can do the same thing. You can write transition amplitudes, and the transition amplitude of quantum mechanics in the semi-classical limit are given by exponential of the Hamilton function over h bar. So I'm going to have the form E I S over h bar in the classical limit, in the small h bar limit. And this transition function, again, can be viewed as function of all the variables without needing to distinguish the dependent and independent variables. And this is how we can do both classical mechanics and quantum mechanics without need of distinguishing the dependent variable time and the independent variable time by having just a bunch of variables evolving together. So in other words, forget time in the sense of which one is a time variable. Well, you don't need to say which one is a time variable. You need to say how variables change together. There's a clean classical quantum formalism for doing that. That's the way quantum gravity will treat temporality. So this was just a conceptual introduction. So next week, slowly, the task will be to build this W for the spin network. And I'll build explicitly this amplitude for the spin network. And the final task will be to prove that in the classical limit, this has this form where S is a Hamilton function of general relativity, which is known explicitly. It's non-explicit in the sense of not explicit with respect to its as a function of its what it depends upon, but we can write it formally, and we can prove that the W of loop quantum gravity is related in a similar way to general relativity. Have a good weekend. Don't have a good weekend. Question first.
So the Hamilton function formalism is not completely equivalent to the Lagrange one, then?
These various formalism, Lagrangian, Hamiltonian, Hamilton-Jacobi, etc., they are never exactly equivalent. You can always find cases in which you can do one and not the other one. So they are equivalent in all the simple cases you can think about, but then you can devise cases in which they're not equivalent.
Yeah.
And there are crucial ones in which you can do one and not the other.
And it's not that one is more general than the other. I mean, there are cases in which you can...
No, I think you can always... No. The Hamilton-Jacobi is more... Well, this way of doing Hamilton-Jacobi is more general than the Lagrangian.
So you can always go back to the Lagrangian while you cannot go to the Hamilton one.
No, it's the opposite. There are but I may do an example because it may be a good, useful example. There are cases in which you can have this covariant formalism that I just hinted at, and not the non-covariant formalism. So you cannot do a Lagrangian, a standard Lagrange evolution in time. You can do something else. Then in turn, there is a Lagrangian formalism, is a parametrized Lagrangian formalism. So you can twist the Lagrangian language to include more general cases. But the Hamilton is like the Hamiltonian formalism, right? The Hamiltonian system that don't have an analogous Lagrangian system. So it's more general. Good.